Thank you very much for the invite. Really a great opportunity to come here and be part of this wonderful setting. And aerospace has had a few projects, small projects with the Getty Museum, and we had some visitations back and forth. So I think, like Mikhail said, the presentation I'm going to give is not on cultural heritage, but you can see the applications that may transpire. Quick overview. This is a presentation that was cleared. It takes a lot to clear a presentation, so it has 3 modules. I'm only going to speak about the third one because of the time constraint of this presentation. However, a quick background on the Aerospace Corporation. It is a federally funded research and development center, FFRDC. There are about 35-ish companies like that in the United States. Each one is dedicated to a specific sector, if it's energy or aviation or other transportation. Ours is dedicated towards space, and we are connected directly with the Space Force. We have oversight on the space programs, the space manufacturers, satellites or launch vehicles that have contracts with the government. That would be the Space Force. We monitor what they do. We make sure that they're doing the right stuff. There's a conflict of interest internally. If a company is building something and they have a problem, then they can make a quick fake solution. So we have to make sure that what they're doing is correct. And sometimes when they come to a situation that they cannot solve, they say it's undoable. We often walk in and provide them with a solution. And so we have a very strong technical background. The company has about 1,000 PhDs, different disciplines. And my area is non-destructive testing. We're material scientists focusing on non-destructive testing. And that's where we contribute. Besides the defense, besides the Space Force, we also have civil and commercial contracts. So civil contracts would be government that are non-defense, like NASA. And that's the example that I'm going to be talking about today. And commercial is non-space related. One of the projects I had was developing inspections for railroads. So I'm going. So we'll start from here. We'll start from here, which was case number 3 for me. This is kissing on bonds for heat shields. These are the heat shields for the Orion capsule. So NASA has plans to go back to the moon. Originally, the plan was they were going to land on the moon in 2019. But they had to build this big rocket. It's called SLS. They had to build a launch pad for it. They had to build a capsule that's going to carry the astronauts. They have the astronauts picked since before 2019. We think we're going to land in 2025, which is a realistic goal. And these astronauts, of course, got older by 6 or 7 years, more experience. This is the capsule right here, and it's me doing an inspection on it. The capsule is here, it's upside down. This is the bottom part of the capsule, it's composite. And they put those heat shield tiles on them, these brown squarish pieces. Each piece cost $1 million to make. So they bond these pieces on the composite. They know they're bonded, but they don't know if you have islands of unbond between the tile and the substrate, which is composite. So we call this a kissing unbond, which means the glue is there, the adhesive is there, but we don't know if the bond is there. They do X-ray, backscatter X-ray. They did terahertz imaging. They did a lot of other techniques. All the imaging techniques will show you the adhesive layer. They don't tell you if it's bonded or not. So to inspect for a bond condition, you need a mechanical wave like ultrasound to interrogate this. But this material is very inhomogeneous, very scattering to sound, very attenuating for sound. Sound does not go in. We need to do a one-sided inspection. That means when you get the sound in, it has to come back. That's a round trip through a material that doesn't want to take your sound wave. NASA tried for about 18 months, and finally when they called us, we knew exactly what we were going to do. We had some prior experience with stuff like that. I think I mentioned all these things. We had some prior experience with all of that, and we asked them to send us a piece so that we can demonstrate what we can do. They sent us a piece that has one kissing on bond circular area. They took the adhesive, they pre-cured it, they put it down, and then they put the rest of the adhesive and cured it together. So the pre-cured adhesive did not bond. But when you do X-ray, when you do terahertz, you see no air gap. However, the part is not bonded. They also did contamination. They do contamination on the part, and they bond their blocks. What they discovered is that terahertz can see the contamination, but not necessarily the unbond of the contamination. So when we did the ultrasound, we showed them that part of the contamination was bonded and part of the contamination was not bonded. So terahertz was finding the contaminant, but not the bond condition. And so we had to do a lot of, we knew that NASA tried, and NASA, not just NASA, one center of NASA, a lot of centers of NASA tried. A lot of other companies outside of NASA also tried, Lockheed among them, other companies, universities. They just could not do it. So when they brought the piece, we had to basically use tricks. We had to compromise intellectually or intuitively. We had to compromise some things that we wouldn't do to get the sound in, and then we had to do some signal processing to regain what we lost in the compromise that we did. So that was basically the philosophy behind this. And we're going to talk about several of these steps that we did. The first one is that ultrasound needs to be coupled to the surface. So we usually use gel or water or something, but this surface, we were not allowed to use anything other than water or alcohol. When we asked, they said alcohol is okay. Water beads up on the surface, does not wet the surface. Their philosophy was to soak this part for 2 days in the water, and then you can inspect it, but that works only on a block. It doesn't work on the entire capsule. We added alcohol to the water, so it was 50-50 cocktail of water and alcohol that broke the surface tension, but water also seeped into the block, and that allowed the sound wave to go in with the water into the block, and immediately we had a sound wave going inside this part that was very resistant to any sound wave. This impedance matching, basically, the water density is the block density is from wet to dry, so that density is gradually changing. The sound will go in very gradually into the part without hitting an impedance, abrupt change in the acoustic impedance, and when you have an abrupt change, the sound wave will reflect and not go in. So it gradually went in and gradually came back out. So now we have a signal. The second thing that we had to do is that we have to use low frequency because high frequency will attenuate. So using low frequency, we get the sound in. But low frequency doesn't have a good resolution. So to get the good resolution on the low frequency, we had to use a very rare, very high damping transducer, meaning that the transducer doesn't ring, doesn't have that ringing that is usually associated with low frequency transducers. We had a very high damping, pulse-like shape signal that went in. The other thing about low frequency transducers is they tend to be big, so there is more energy that goes into the material, but because they're big, their spatial resolution is not good. So now we lost two resolutions, temporal and spatial resolution. But the high damping got us the narrow pulse that goes inside. And as I show on the schematic, we got we can distinguish between the two echoes, one returning from the bond line, that lower green, one returning from the bond line right there, and one returning from the back wall of the composite. These are these two echoes. With high ringing transducers, these two echoes will blend together. But because we got two distinct echoes, what we could do now is we can take the ratio between these two echoes. And if I go back, these two echoes experience the same path. They both went through this brown part. They went through the same part, which is very inhomogeneous. So when I take the ratio between these two echoes, all the inhomogeneity under the transducer will be normalized. And the only difference will be is the condition of the bond line and the condition of the back wall. Condition of the back wall being almost consistent, and the condition of the bond line is either bonded or not bonded. So these are the two echoes. When you gate the signal on the first echo, you gate the signal on the second echo, take the ratio. This is the image we get. Now, this is not a random scan. This is a very repeatable scan. This cloudiness and murkiness represents the inhomogeneity of the part itself. So this is very repeatable if you scan it several times. And but when we take the ratio, this is M1 is the magnitude of the first echo, M2 is the magnitude of the second echo. When we take the ratio, you start to see something that emerges. The blue being the kissing unbound circular disc that they put in, and the other one on the right is a pull tab. Basically, they put a metal shim, they bonded everything, they pulled the metal shim, so it's an air gap. So they wanted to see the difference between the two. So we got this. This is far more advanced than any signal NASA had ever got. And this will be the worst picture you see today. So this is the first step, is that when we took the ratio, we immediately saw that the inhomogeneity actually got normalized. We see the two areas of unbond, and we wanted to improve it a little bit. So this other thing is what we call a phase shift. Basically, the coefficient of reflection depends on the difference of the acoustic impedance between the first medium and the second medium. And so when you go from high, here's the equation. It's the acoustic impedance of the second medium minus the first divided by the sum of them. And the impedance is basically density multiplied by velocity. When you go from high to low, and then you come back from low to high acoustic impedances, that echo amplitude may be the same, but the sign Z1 minus Z2 versus Z2 minus Z1, the ratio is the same, the absolute value of the ratio is the same, but the sign will be different. One of them positive, one of them is negative, and this means that we get, here's a positive and negative, that means we get the same amplitude, but the phase of the signal will shift. And so let's take that, and we do a phase map. When we did a phase map, we have to use an arbitrary initial phase of the signal coming out of the transducer. We choose an arbitrary signal phase value that will give us the that'll give us a 0 right here at the edge of the defect. At the edge of the defect, your transducer, center of the transducer on the edge of the defect means half of it is positive phase and the other half is negative phase. They zero out. And so we choose that arbitrary value. This is part of the calibration, and gives you this 0 at the edge, this yellow halo. And then we take the cosine of that signal and threshold it at 0. Everything above 0 becomes white. Everything below 0 is black. And you have a black and white image of the good and bad areas. We're still not happy with this because there's a lot of junk up there. So we decided, because the signal is not very consistent, sometimes very strong, sometimes it's weak, we decided to include that into the analysis. So when the signal is weak and I take a phase value on that, my confidence in the phase calculation is not very strong. When the signal is very strong, the amplitude, and I take a phase value, my confidence is stronger. So we multiply the phase map with the amplitude of the signal. That way we can enhance the values coming in from a strong signal and decrease the contribution from weak signals. We also have a transducer, while it's sitting at the same spot, it's averaging continuously and cleaning up the signal. So at that, we multiply the amplitude by the phase. We get this image right here on the right. So the circle is getting better, and the square, the rectangular shape is getting better on the right. And then remember, we use a larger transducer, so we lost some of the spatial resolution of the signal. What we did next is what we call, some of you may be familiar with it, synthetic aperture focusing technique, which means as a transducer sees a specific point for multiple positions, we can use the focal laws and work them backwards, something like this animation that I have on the bottom. So as transducer looking at the same spot from different positions, and we can synthetically create that focal law that you see on the far right. And this will sharpen the image. So we do that. All these images before SAFT become this after SAFT. And in the end, you use this one. This is exactly what the defect area looks like. The rectangular pull tab and the circular kissing bond, and here the black and white. This is the technique that we delivered to NASA. We also purchased the ultrasonic scanning equipment from the vendor that allowed us to, that gave us the code to their machine so that we can reprogram the machine, because we wanted all of this to be done in real time, not post-processed. And we also attached string encoders so that the technician can use freehand with 2 strings attached to a transducer. That way, the 2 strings will, each one will give you the length of the string, and we can calculate, triangulate the position, and have a monitor displaying in real time, just like a coloring book, the areas of good and bad. So something that was extremely, almost impossible, we made it as easy as a child's coloring book. We published this in Materials Evaluation, a special issue that was dedicated for Orion, because we put 3 papers in there, and the first one received an Outstanding Paper Award. I want to acknowledge my colleagues, Dr. Young Kim and Dr. Toby Case. Toby Case did most of the work, he and I. Young Kim, the acknowledgement pertains to the other 2 cases that I didn't present. And I hope I kept it within the time allotted. Thank you very much.
Thank you very much for the very interesting presentation. Any questions from the audience? Yes, Cecilia?
Thank you very much for your presentation. I wanted to know how long did you take to solve the issue since you received your sample from the NASA?
That first image that I told you, the worst one, was in half an hour. And the concept that I presented was in 1 week. And it took us 2 years to build the full computer program training, buy the machines, the scanners, and pass what we call 1995 probability of detection, POD study. So that took a long time to take it from, NASA has, I don't know, some of you may be familiar with TRL levels, technology readiness levels. So TRL level is 9 is where it's commercial, you can use it. So we took it from an impossible to TRL 9 within 2 years.
Very impressive.
Thank you.
Any other question?
Yeah, this was a very nice experiment. So this was optimized for a particular application where you had a given thickness. How thin could the tiles go and you'd still have enough separation between the pulses?
So in this case, the challenge, the thickness of a tile is, the thinner is better because the tile is very attenuating. The challenge was not in the thinness, in the thickness of the tile, because the next phase, they gave us tiles of changing thicknesses, ramping up. So the echo is actually not hitting straight down. When you have the substrate is flat and the tile is at an angle, that echo is going to go at an angle. So we had to capture it somehow. So, and then it got thicker and thicker. We worked on 1 inch. Ultimately, at the thickest positions, it's 3 inches thick. So that became more challenging. But when I say it took us 2 years to resolve all the issues, it's including this problem of the changing thickness, the ramping, the curvature, and the thinnest. Excuse me. The thinnest here is about, I think, 1 inch or 3/4 of an inch that we had to deal with.
But if you went to a millimeter, you'd have other challenges, I guess.
If you go to a millimeter, it's a completely different problem. We work with composites a lot, with corks and other, and we do deal with 1 millimeter thickness layers. We would use a 15 and 20 megahertz transducer instead of half a megahertz transducer because you don't have a lot of attenuation. You just want to penetrate and get, so it's a different problem to deal with. I wouldn't be using this technique.
And it's all longitudinal waves, right?
Yes.
Any other question?
Thank you very much.
I had a curiosity.
Oh.
Maybe it's not exactly what you showed, but did you also do some simulations on the thermomechanical response of the system, like when it's unbonded? What are the damage mechanisms that develop?
Oh, the damage mechanism?
Yeah.
That's a very big task that they are working on it because NASA did fly this capsule without astronauts. When it came back, these tiles were somewhat charred as expected. So now they are doing analysis on the damage mechanism. What's the extent of the charring? Is it going to ever be a problem? So it's not an easy material to work with because all of our analysis, we know how to work with steel, with aluminum, with composites, with foams. And this one is a completely proprietary, weird material. And so there is a big effort on that. Like I said, it's a little bit complicated. But as far as simulations on ultrasound and all the inspections, we do have, of course, people that do this for us. In the end, the simulation may not give you the problems that you actually deal with and experimentally, especially when you come to these weird materials. The presentation that I had, the 3 cases, they're all difficult, weird materials. And so simulation sometimes has to learn from the experiment versus the other way around. Yeah.
Okay, thank you very much.
Thank you.
So let's thank again the speaker,
Thank you.
our speaker.